This is the video version of the Unit 4 Section 2 Notes Part A on Kinetic Molecular Theory, Intro to Gases, and Variables. In this slideshow, we're going to talk about kinetic molecular theory, especially as it relates to gases. We'll also talk about the variables related to gases, such as pressure, volume, number of particles, temperature, and we'll discuss what STP means when it comes to gases. So first, kinetic molecular theory. What this states is that basically all particles, atoms, molecules, are constantly in motion, regardless of the substance we're looking at. So for instance, solids, even though the particles are ordered, they do vibrate in place and they have that organization. They're close to one another, but they're still vibrating. Liquids, those particles are moving a little bit more now. They're vibrating, but they also flow past one another. Notice that those particles still stay connected. Gases, on the other hand, this is when particles basically bounce around the container or space that they're in. They are technically vibrating, but it's not wrong to think of them like, say, pinballs bouncing around a room. Now, kinetic molecular theory, as we will discuss it, will focus mostly on gases. There's a few assumptions we have to make. First, that gases have many particles that are spread far apart. Gas particles are constantly moving in random directions. Also, gas particles are not attracted to one another or the container. That's a really big one. That is an assumption that will break down if you analyze gases at a very fine detail, but for us, that is generally okay for a lot of gases. Also, we're going to assume here at the end that the average kinetic energy of the gas is dependent on their temperature. This really is the definition of temperature, and we'll talk a little bit more about what kinetic energy means in just a bit. Now, as far as variables, when it comes to gases, we use a lot of different variables for our different measurements. They have different units. First, we're going to talk about pressure. We're going to symbolize that in general as P. While there are multiple units for pressure in this class in chemistry, we're going to stick with ATM, standing for atmospheres. When it comes to temperature, we're going to use the symbol T. And although we use Celsius and Fahrenheit a lot, temperature in terms of gases, we're always going to use it in Kelvin. And we'll describe what that is in a little bit. When it comes to volume, V, you can see the symbols are all matching those names. Volume is always going to be in liters when it comes to gases. And number of particles. Remember that as chemists, there are tons of atoms or molecules in your sample, so we're not going to count number of particles, we're going to count by moles, and that symbol is going to be N. We cannot use M because that is already used for mass. So the symbol here is N, meaning number of moles. And that's always in moles, abbreviated as MOL. Now, pressure. What pressure is the force, as far as a gas is concerned, it's the force exerted by a gas per a unit surface area of an object. Really what this means is it's both the force that the gas is pressing over a certain area. Pressure in general, you can kind of imagine it as like, say, a knife cutting a steak. The knife is still the person's arm pressing down, that's the force, but because the blade is so sharp, it cuts through. The pressure is a lot higher because the area is much smaller. It's also why you can't cut a steak with a spoon. They're still pressing down with the force of their hand, but the spoon is a lot more blunt. Because the area is greater, the pressure is lower. So a smaller area means higher pressure. Also, higher force means higher pressure. Now, what is this in terms of gases? Well, gas pressure is really the simultaneous collisions of billions of gas particles with an object or the walls of a container. We wouldn't experience any one of these collisions shown in these pictures. We would just observe the overall effect. We would feel the gas particles pressing on the outside of the container, but we would feel it in a large-scale sense. For instance, if the wind blows against your skin, you are literally feeling the gas molecules of air hitting your skin. It's just that they're so small that they look like, or they feel rather, like one force or one pressure. Now, a couple scenarios here. Let's say we take a gas in a piston, and we can see a larger volume on the left and a smaller volume on the right if we, say, compress this gas. As the volume decreases, the pressure will increase, simply because as you make the chamber smaller, these particles are going to more often collide with the walls of the container. Similarly, if you have two samples and one has significantly more gas particles, As we increase the number of particles, the pressure will also increase because you're simply going to have more particles hitting the walls more often. Now, pressure has many units. A couple of them we see in everyday life are, say, PSI, which you might see in tires, balloons, or some industrial applications. You might see millimeters of mercury. We see this in medicine and biology, also in blood pressure cuffs shown on screen. And sometimes you'll use this for weather conditions, for atmospheric pressure. And one other one you might see pretty often is kPa, standing for kilopascals. You'll see this in engineering and material science, also in some industrial applications. All of these are pressure units. However, in this class, as mentioned previously, we're going to stick with atmospheres. We use these across many of the sciences, and also they are used in weather applications. The reason being is because if you picture this as a column of air, you can notice that the air is basically pressing down on the air beneath it, making the air a little bit denser down towards the ground level. We say that one atmosphere is the pressure at sea level. So it's standardized based on the atmosphere. Now let's talk about temperature very briefly. Temperature is the average kinetic energy of the atoms or molecules in a material. Now, kinetic energy is technically a formula where its kinetic energy is 1/2 times the mass of something times its speed or velocity squared. You can see that over here on the left. Both speed and mass affect temperature. So if you increase how fast your gas particles are moving, as well as their mass, both of those will lead to a higher temperature. However, for us, it's more realistic just to say that temperature is basically speed. If we just think about one gas, the faster the particles move, the greater the temperature. Also, as a quick side note, notice that it is the average kinetic energy. If you observe this sample of gas on the right side, you'll notice that some particles move slow, some move fast. The temperature is the average effect. Now, temperature. We usually use two scales in everyday life. We use Fahrenheit. This is our common scale in the US. We also use Celsius sometimes, especially in science classes. This is based on the freezing point and the boiling point of water. Water freezes at 0 degrees Celsius. Water boils at 100 degrees Celsius. However, with gases, we have to use a new scale. We have to use the Kelvin scale with the symbol K. It goes up by the same amount as Celsius. 1 degree Celsius is basically the same thing as 1 degree Kelvin as far as changing temperature. However, Kelvin is based on the point where all molecules stop moving. 0 Kelvin is the lowest possible temperature. Luckily, to convert between Celsius and Kelvin is easy. If you want to figure out what a Celsius degree is in Kelvin, just add 273. For instance, if it was 100 degrees Celsius out, it would be 373 Kelvin. And backwards, if we wanted to go from Kelvin back to Celsius, you would just subtract 273. We won't do this very often. There's not much of a point. Quick hint, remember that since Kelvin cannot be below 0, if you get an answer that's negative Kelvin, it does not make sense. Now, with temperature, let's say it's an especially hot day at 35 degrees Celsius, and I asked, what is this temperature in Kelvin? Well, take your temperature in Celsius. I'm plugging in 35 for the Celsius, keeping the 273 the same. And when I add it up, I can see that this is 308 Kelvin. Now let's say hypothetically you wanted to go from Kelvin back to Celsius. If we had 63 Kelvin and I asked what is that temperature in Celsius, I would use my other equation, Celsius equals Kelvin minus 273. I'd plug in Kelvin. 63 minus 273 is negative 210 Celsius, showing us that this is a very cold temperature. It's negative 210 degrees Celsius, and you can have a negative Celsius temperature. That is okay, but you can't have a negative Kelvin temperature. 0 Kelvin is the lowest temperature. Now, one last note on standard temperature and pressure. Standard temperature and pressure, often abbreviated as STP, is just a standard set of conditions that we use in science, sort of like shorthand. It is equal to 0 Celsius, 273 Kelvin, same thing, and 1 atmosphere of pressure. And this is just a way for us to basically compare different gases if we compare them at STP. And those are the notes for Unit 4, Section 2.